Good evening, good morning, good afternoon, whenever you're watching this. Hi guys, good to see you again. I think I start off every lecture so annoyingly, right? Trying to have a set. I want to have a set structure to each of my lectures. Good news. Let's just jump to the good news. This lecture is actually going to be quite a bit smaller. We're just kind of finishing up 1.3, and then we're done with it. And then we will be having a quiz or test over this material over Unit 1. So do be prepared for it, right? We'll kind of go over that at a different time, but just know we're close. We're done. We're wrapping it up. Do know on top of that there is there's a little bit more reading for this section. So please make sure you do your reading. I can't stress that enough. Hopefully, if I don't, I'm just reminding myself to tell you now. If I don't say it in one of my meeting calls, just because it's very vital to understanding all the concepts. We just don't have enough time to go over it. So please make sure you do the reading that I assign from living in the environment. All right. Kind of the last part is we're talking about systems. We're kind of finishing up the idea of systems and looking at things in a diagram type of way, right? Just to kind of re-stress some of those key points. What are systems, right? Think about what are systems. Remember, there are many pieces working together to do a function, right? They work together and they do something that is, kind of like a team in a way, right? There's many subsystems within systems. Do remember that. And then also the definite requirements of systems. You need inputs, outputs, processes, right? Stores. And then really, there's different types of processes that don't necessarily need to be in all systems, but at least one of them will need to be, right? So that's key to remember. I like to think of systems as this thing of, think of a huge motor, right? Think of the world as this huge motor. You have maybe your biology system or your ecology system or nature. You have your butterflies, your bees that do their certain function, and then they pollinate the trees, then they have their function. There's all billions, if not connected, little gears in this world that are each individual systems, right? But you need all the gears working together to make a well-oiled machine, right? What we're kind of getting at is when you start messing with one of those gears, let's talk about maybe temperature, right? Global climate change. If you start messing with temperature, if you make it bigger or smaller, it's going to have these big consequences on all the other gears spinning within that big motor or watch. So kind of think about it like that when we're going to this process, right? I really want you to understand the basics of this and really have a good argument for it. I can't stress that enough. AP, I think I don't want to get you guys worried, but I'm really stressing the fact that we really start building into more of the AP kind of structure, right? The AP requires a lot, in regards to essays, or if you're writing an essay or you're giving an example of something, you have to do your research. You have to have good, strong arguments towards it, right? So when we're talking about systems, have a general assumption of that the structure of systems, that you can use these as examples and it will help you out. Okay, kind of on the last part to kind of now move in. I already talked for about 4 minutes, but okay, group thought or think to yourself and pause this. But what do all these pictures below have in common? Boom. Oh, it doesn't give the answer. Well, they're models, right? System diagrams are models of real systems. That's kind of what we're getting at, right? Like even like back to this one where we have, this is a systems diagram of kind of what happens in real nature. That is kind of like this, a little bit more just, visually, right? These are models of what is going on in the world around us. We use these in environmental science. These boxes, these arrows as flows. You sometimes use different colors for the arrows to represent different things. But when we're talking about models, just know that there are some good things and negative things, right? Good ways, you should be keeping this in mind. Why do we use these diagrams? Well, they're easy. They're an easy way of understanding complex issues, right? To understand energy flow through a food chain. We use that type of simple model to kind of show us that system diagram. Now, what's bad about it? Well, we can't get all the working pieces. If we try putting all the working pieces in there, it would be this infinite amount of information. So there are good things and there are bad things. So I just want to stress that system diagrams are a model, okay? Now, we're going to talk about three main systems. We have what's called open systems, closed systems, and isolated systems. Open systems are by far the one we're going to talk about all the time in this class. And for your notes, you might want to put this down, but open systems, they can exchange matter and energy with its surroundings. So I'm going to use our bodies as an example, right? Our body is an open system. We take in food, that means we have matter coming in, right? We also maybe absorb sunlight, right? We take in energy, we take in matter, and then we expel those things as well, right? That is matter going in, matter and output. Energy can go in, energy can go out, right? That is an open system. So anything that has kind of energy going in and out is an open system. Now, once again, everything we talk about in environmental science is really going to be an open system. We'll get to closed systems next, and there's only really one we talk about, and that could even be argued whether that is an actual closed system. But in this regard, for AP Environmental Science, they say it is, so we must go with that. I'll explain that in a second. But just know that all these systems have energy coming in, energy going out, matter coming in, matter going out. So think of a tree as well, right? Tree has heat that it absorbs, that's energy going in, then it might release heat, right? Energy going out. It also takes up nutrients, which is matter, and then then it releases that nutrients through, maybe it builds up tree, then leaves fall, right? That matter is going out in a process. So do know that key point. And how it looks in a system diagram is like this. It exchanges matter and energy with its surroundings. Energy going in, mass going in, mass going out, energy going out. Once again, nearly everything we'll talk about in this class is an open system. Closed systems, on the other hand, exchange energy but no matter. So energy comes in, energy can leave, but matter doesn't come in and matter doesn't leave. Okay, and the example that we use in AP Environmental Science is Earth. Earth is a closed system. Now, I'll argue this because being a big science buff and dealing with astronomy and everything, back in Earth's history, Earth has gotten hit by meteors, right? So that technically could be matter coming in, and it has left water on this planet, but then it dissipates. Actually, we are losing very small, minuscule amounts of gas and water out to into the universe. But don't put that. If it comes up on a test, Earth is our example of a closed system in Earth science or environmental science, right? So it has energy coming in, no matter coming in, no matter going out, right? So the example here is Earth has energy coming from the sun, and then it bounces back out into the universe, right? That's its example. Another example would be Biosphere 2. And in this lecture, you're going to watch this now, hopefully this video. I can't stress this enough, but Biosphere 2 allowed light to come in, light to go out, but it never let any gases in, no solids, no liquids into it, and then expelled. It wouldn't let those leave as well. So technically Biosphere 2 would be a closed system as well. So now here's the time. Please watch that video. I've attached it to the Google Classroom. Please, you must watch it because it'll pop up on you. You might have to write an essay in regards to it, or maybe not an essay, but at least answer some questions in regards to it. So, and it fits environmental science so well. So please go do that. Or you can wait till after this lecture. I'm almost done. All right. The final one. Closed system. No, this is a closed system. It really just shows what Earth is Biosphere 2. But once again, this is just the systems diagram of it. We have energy in, energy out, but no exchange of matter. So now there's matter in the Earth, of course, right? Earth has tons of matter in it, but no matter is coming in, no matter is going out. It's staying in that store, right? So it still has matter, just no exchange of it. Finally, is an isolated system. This is the final system. We won't talk about this one, but you do have to know what makes up an isolated system. They don't exist naturally, and the only one we can kind of think of, and we don't fully know this for sure, is the universe. The universe is an isolated system. Maybe nothing is going out of this universe, nothing is going in, right? So universe is pretty much the same thing. Nothing goes in or out. Whatever's in it is in it. Nothing is being exchanged. So isolated system is kind of a trick question. It's just the universe would be our only example of this, and maybe not even that, because we don't quite know those possible interactions within universes, dealing with alternate realities, alternate universes. We don't know, right, fully at this point. So that is your example there. Models of systems, right? I kind of went over this as well, but a model is just a simplified description designed to show the structures of working of an object, system, or concept, right? It's just an easy way of viewing how how these entities or these different parts work together to provide a function. That's really what this is. And there's, universal system models. They all kind of have the same look. If you're drawing a systems diagram, it should include stores, whether that's a circle or a box or a drawing of a lion they use, right? It should have that, but it should have flows, arrows pointing towards the way that energy and matter flows throughout the system, right? That is key. And this is just for those of you who are joining the IB program next year. So like the goal, right? We have inputs. You have a goal coming in as the input. You have bright individual minds going into it, right? Then there's the process, what you're learning and maybe taking in homework. And then there's the output. Maybe you pass a test or you get that accreditation. Same thing for AP, right? I just put IB here just because you guys might be going to that, right? And then it may follow up into kind of a circular system model. So, what would be the example of storage in this scenario? Where are the stores, right? Hopefully you can kind of think about that. But usually the stores are where the processes are happening, or a store would be like the individual minds, right? That is a store. That's where varying processes are going in, but then it goes into this process. Then you combine it with teaching and learning. So each of those individual boxes are stores there. The final part to this is very important. Please make sure you listen to this because this will probably pop up on your final hint. Those of you who are listening closely to my lecture videos. We have positive and negative feedback loops. These are huge. We're going to be talking about these constantly throughout this year. Positive feedback loops enhance or amplify changes. This tends to move a system away from its equilibrium or balanced state and make it more unsustainable. So technically, this is going to get confusing, but positive feedback loops just mean positive input, more added to it, or a change in the system. That means it's a system that is out of whack. Every time it goes through its circle, it increases or decreases as it goes around. That is more than likely a bad thing when we're talking about nature. Think about global warming as a perfect example of a positive feedback loop. You have heating of the earth, right? That tends to melt ice caps a little bit more. So you have more melting ice caps, which then gives off less reflectivity. So then you have even more heat the next round. And then it melts even more ice caps. Then the process keeps intensifying. So when we're talking about positive feedback loops, they're actually quite harmful to the environment. We'll talk about those in later units, but you must know that for this one. A negative feedback loop, on the other hand, tends to dampen or buffer those changes. So if there's a change that's happening within it, there's other things that happen to keep it balanced. So nature tends to want to be a negative feedback loop. It tends to want to be balanced. So in your mind, once again, positive feedback loops tend to be on a bad side in regards to environmental issues because they're compounding the problem. It gets worse and worse and worse. Or negative, there might be a problem that happens in it, but then it refixes itself. An example, I believe I have it here. Here's a negative feedback loop. Nature wants to stay in equilibrium. So we can start anywhere here, but let's say we have 3 lynx. Well, there's only 3 rabbits. There's not enough food around, so the lynx die. So then when the lynx die, or the big cat, more rabbits are grown, right? Because it has less predators. And then when there's more rabbits, more cats can form, right? And then it keeps its nice balance throughout the system. Even though one thing changes, it keeps this nice steady balance about it. Nature always wants to do this, right? That's why you don't see billions of grasshoppers on this planet. Well, there probably are billions, but a bad example, but I mean that's why the world is not covered in grasshoppers, right? Because there's certain things that stop it from getting out of hand, right? There's just only a certain amount of food or a certain amount of water, so it keeps those numbers in check. When you do have this explosion of maybe cockroaches in an area, well, they tend to eat everything, and then there's a mass die-off, and it brings it back into check. Nature is like this. It wants to stay balanced. Positive feedback loops, I think I already kind of gave this one to you, right? But we have this initial warming that's happening. So Earth's temperature is rising, right? Then we have a decrease in the amount of ice. And then that ice, just the albedo or the reflectivity of that ice is less. So then you have even more sunlight being absorbed, which then causes even more heat. And it gets worse and worse and worse. And we are going to definitely talk about positive feedback loops in the future. Okay, but it's important to understand that positive feedback loops are ones that just keep intensifying. Negative feedback loops tend to try staying stable. Okay. All right, ladies and gentlemen, see, that is it. I kept it under 15 minutes. Please watch that video. Enjoy it. I think it is a good one. Really stresses these points. But once again, guys, we're kind of moving past the introduction phase. AP Environmental Science is going to get a little bit more tricky, okay? Stay up with it. Let me know if you have any questions. I'm here to help to understand these critical things. But if you're watching my lecture videos, hopefully you understand the main points of them, right? All right, take care. See you later.